Welcome all to Module 3, and this is the first lesson of that module. So in this module, we're looking at overcurrent protection, and then we are going to combine that into a whole system where we look at a radial system and how you would apply overcurrent protection through that system. Protection against excess current was one of the first forms of protections that were developed. And the reason that it was developed is because when they just looked at your discrimination by time when you had a radial system, it didn't work so well. It had disadvantages. And then when they looked at discrimination by current magnitude alone as well, there were certain disadvantages. So what they did is that they combined the two systems so that you could have discrimination by time and current magnitude. And this is really what this chapter is going to be looking at. So we call this situation then a time-graded overcurrent protection system. And really what happens is that you've got a time lag. In other words, there must be a delay in the manner that the relays are going to open for the same fault that they see in the system. And what you're wanting in your timing is that the relay closest to your fault must hit it first, and then the relay that is furthest away must first delay before it can be able to take out that same fault. So we have a relay that was then designed for this type of situation, and those relays are called an inverse time current characteristic. This is a little bit of a recap of what we learned in chapter 1 by discrimination by time. So if you're looking at the system on the left-hand side, you will see that you've got a source point, then you've got about 5 bus bars, and there are 2 transformers that you have in the system. And then this shows that you've got a fault that is sitting between B and A. So then in this scenario, if that fault occurred at that point, then you expect that your relay at B would be the first relay that operates to clear that fault. And should it fail to operate, then your C would come in next. And if that failed for whatever reason, then it would be your D, and your E would be the last one to be able to do the operation. So this is what we call discrimination by time. The first one closest to the fault is the one that operates, and everyone else is going to have a delay before they operate for that fault. Then we looked at discrimination by current magnitude. And what this really does as a system is that it looks at your line length, which we then say is really proportional to your impedance. So we measure the impedance of your system, and then depending on certain points of your system, we calculate what that fault current should be, looking at the impedance so that we can then set our relays to act accordingly. Now, there are things that are not practical about this scenario. So if you look at F1 and F2 on our left-hand side, you will see that F1 is between C and B, and F2 is between B and A. But with F1 and F2, when you try to put this discrimination to work, it doesn't work so well because the distances really between F1 and F2 are not that great. And the thing that makes it then difficult is that if F1 had to have a fault, you expect the relay at C to be able to kick in. And if F2 had to have a fault, then you expect the relay at B to be able to kick in. So if you can't have a proper discrimination between the two, that means C will act for a fault at F2 as well as for a fault at F1. Also, this system looks at your fault levels between all your various points. So if you had to look at your source where you've got 250 MVA that is put in there, if you had to have an issue with that cable between your C and your B point, then just looking at that fault level, you would not be able to protect that cable because it's set at a very high current that looks at really your source. Then your discrimination by time and current put together. So because the two systems that we looked at had fundamental disadvantages, where in your discrimination by time, we had the disadvantage that your more severe faults are going to be closer to your source and they will take the longest time to be able to be cleared. And then on your discrimination by current, where we had to appreciate the impedance between any two breakers before your circuit could be able to work properly. So a relay was developed that looked at both your time as well as your current, and it combined the two characteristics together, and we called it the inverse time over current relay. So what it does is that for a fault current that it picks up, it must take the shortest time in order to be able to take out that fault in it. I am now going to introduce what we call the IDMT relay. IDMT stands for Inverse Definite Minimum Time Relay. So this relay is what is used for the time and current characteristics. And really, as I said before in the previous slide, that your inverse means that as your current increases, your time is going to decrease. So therefore, as your current keeps increasing, the relay must take its minimum time in order to trip the circuit. So the higher your current, the less time your relay must take to trip it out. Then you've got your definite minimum. It means that it appears to approach a definite minimum time for it to be able to act. So three of these IDMT relays have been evolved over time. The first part that we had was your electromagnetic types of relays. You still find these in some of the very old power and substations out there. And really, when we start talking about practice, they're the one that makes the practical calculations for us easier because we can understand how they operate physically. They use electromagnets of coils and your magnets to control the on and off position. So when a fault occurs, your excitation current will energize that coils that you have in there, and they will cause your magnet to either open or close. So therefore you will have your on or off status in your operating circuit. Then we had your static, or what we call the electronic relays, coming in second. And really, these relays, what they would do is that they use an analog system. Now, we know an analog system so that they can be able to pick up the readings that are happening from out there and create the relay characteristics, saying that this needs to open or this needs to close. Then you had your numerical, which we also call your microprocessor based relays. Microprocessors are utilized in order to analyze what is happening in the system all the time. And then once a fault is able to be picked up or is detected, then we have that behavior characteristics needs to be programmed into these relays so that it knows that once it picks up this level of a current in the system, this is the function that it needs to do. So on our electromagnet IDMT relay, as I said, it's what we really use for us in order to analyze how these IDMT relays are going to be able to operate. So if you look at the third point in this case, it talks about how the relay really does the operation. It's an induction principle where we have got two electromagnets and they are arranged with such that there is a disk that is between them. And under your fault conditions, the disk rotates until your moving contact touches your fixed contact, therefore closing the tripping circuit. So this is how that standard IDMT over current looks. And if you can see, the top and the bottom on your left hand side are your two electromagnets that we're talking about, and right in the middle is what you have as your disk. So the principle here is that you'll have a magnetic flux that will flow through the disk and causes a current to turn the disk that you have in there. And then once that happens, then that also produces another magnetic flux that goes back into the electromagnets. So you've got two fluxes that will cause then the disk to be able to rotate. If your currents through the electromagnets gets increased, then the speed at which your disk rotate will also increase. So if it's lower current, your speed is very small. If it's higher current, your speed is very fast. And when your disk rotates faster, the time that it travels will then decrease, and it gives your induction disk type relay an inverse characteristic. So if that time then decreases, it means that that space between your two electromagnets will then be closed, and therefore you are tripping the circuit. So in here you have got what you call a plug, and you can see it's labeled from 1 up until 5. So our operating current must get adjusted through that transformer, through those values of 1 to 5, and that really will talk to the operating time of the circuit as well. So your trip time gets adjusted by changing the distance of travel, okay, of the disk for a certain input in current. So that 1 up until 5 will talk to your inputs in currents that you're getting from your actual circuit that is out in the field. When your plug is in position 1, which is right at the top, then your entire coil is in circuit, and the relay is said to be most sensitive in that area. So when that plug is then in position 5, the relay we say is sensitive, and we even say that it is a shorting contact. Now again, this goes back to the slide that we've just come out of. So the 1 up until 5 will talk to what we call a 50% to a 200% plug setting. So 50% is when the relay is most sensitive, which means it's that position 1. And 50% of relay nominal currents are needed from your CT to allow the relay to respond to this. Then at 200% is when your relay is least sensitive, so it means it's at position number 5, and we call it the shorting contact part of your coil. So we say here that 2 times of the relay nominal current is needed from your current transformer to get the relay to respond to this value of your plug setting.